Esters can also do chemistry like this. We call it the Claisen condensation. So here is some ethyl ester. And let's say I'm going to treat it with a relatively weak base, so sodium ethoxide. Notice that this leaving group matches this base. So I don't really need to worry about this substituting with that because they are the same. So I'm going to deprotonate my ester to get an enolate, an ester enolate here. And now when this attacks there, I'll get a product that looks very much like the aldol products that we just saw. It looks like this. As before, I've got some O- that's 2 carbons away from my carbonyl compound. My new bond is right there. So does it stay there? It actually doesn't, right? Because now if I cover all this other stuff up and you look at it, you say, hey, that looks like ester hydrolysis, right? I have that O- and I have a leaving group. I have an OET leaving group. And so is that going to leave? Yes, it is. What this gives me is a beta keto ester. So it's a different, what we call oxidation state than our aldol products. In a usual aldol, this would be just an OH. But now, because it's oxidized, we're starting with an ester instead. Now it's not an OH, it's a CO double bond. So just like before, in an aldol product, I had the OH 2 carbons away from a carbonyl. Now I've got a ketone 2 carbons away from my ester. So it's called a Claisen condensation, but it acts just like an aldol. One version of this is intramolecular, so ring forming, sometimes called the Dieckmann cyclization. So if I take this diketone and now I give it some base, right, the same base as there, this is going to form a ring. How big of a ring? Well, where is my nucleophile? Well, I'm going to deprotonate next to my ketone there, and it's going to be attacking this carbonyl over here. How big a ring is that? 1, 2, 3, 4, 5, 6, 7. 7's a weird number for a ring, but it turns out that this reaction makes 7-membered rings very well. So here's your 7-membered ring intermediate. Again, it would look like an aldol if I didn't have that leaving group here, but now I have a leaving group and it gonna leave, right? When it does leave, I end up with a beta ketoester. One of the ketones is inside this big ring, the other one is outside the ring. And these beta ketoesters look familiar. We talked quite a bit about how these things are easily alkylated. Right? If I do some kind of deprotonation in an SN2 chemistry, I can alkylate here relatively readily. I can alkylate on the other side. I can decarboxylate after either of those. So this is a pretty cool reaction, which is to say here I could this is probably the best way to just make this simple 7-membered ring, is to do it via this cyclization and then decarboxylate to take that group off. So esters do aldols just like the normal aldols, except for, in this case, we've got built-in leaving groups that are going to leave to give us ketones at this position, not alcohols. In our last video, we talked about how esters can act like ketones and aldehydes by giving us a stable carbon nucleophile, a C-, that can go and attack some electrophile. It's worth mentioning that other acidic CHs can do the same. So for instance, nitromethane is a really cheap, easy to handle liquid, and the pKa is 9, right? So that's more acidic than water. NaOH will fully deprotonate this thing. Acetonitrile, pretty stable solvent, but it is slightly acidic, about as acidic as an ester. And if I put 2 cyano groups bridging this thing, I think this is called melanonitrile, this is quite acidic, pK of 12. So all of these things can essentially be deprotonated just like typical carbonyl compounds. So for instance, I can deprotonate nitromethane with simply a weak base like sodium hydroxide, get to this nitroenolate, very stable anion, And now this can act as a nucleophile toward an aldehyde, just like an aldol reaction. Sometimes we call this a nitroaldol, and then some people call it a Henry reaction. So when my nitroenolate attacks my aldehyde, I get this aldol product, right, with a new carbon-carbon bond here and an O- that will then be protonated by water or some other weak acid. That brings me to this alcohol product, again analogous to a normal aldol product. And this, just like a normal aldol, can easily dehydrate under these conditions to give me this unsaturated nitro product. There's a couple cool things I can do with nitroenes like this, but one cool thing is I could use hydrogen and palladium on carbon to just completely reduce the whole thing, right? That will reduce my double bond down to a single bond and reduce my NO2 down to an NH2. So all of a sudden I have a really useful way for me to make ethylamines. And those of you taking neuroscience classes have probably heard a lot about ethylamines, right? A lot of neurotransmitters and have some piece like this. So this is a sneaky useful reaction. My nitrile is going to work the same way, right? Here I might need a slightly stronger base to get the enolate, but here it is. Here are two resonance structures of that conjugate base. When I attack some electrophile, let's say I give it an aldehyde, here's my intermediate. I've made my new carbon-carbon bond here. When I protonate this, I get this alcohol. If I force this under acid or base conditions, I'll lose water, a dehydration reaction, and get to this, now conjugated nitrile. And nitriles are great because now I know lots of reactions I can use nitriles for, right? I can hydrolyze it to a carboxylic acid or an amide. Or I can, as before, reduce it down with hydrogen gas and palladium catalyst. So just like my nitro example, hydrogen and palladium have reduced both the carbon-carbon double bond and my functional group. And so as before, for the nitro I added essentially 2 carbons and a nitrogen. Now I'm adding 3 carbons and a nitrogen. So again, pretty useful for the synthesis of lots of biological amines. To summarize, these are some intermediates that act a lot like enolates. I can make them from things that might not look acidic at first glance, but really are, nitromethane and nitriles. So if I treat these with base, a weak base here, a stronger base there, I can get to some good carbon nucleophile. Again, there's not too many carbon nucleophiles, so it's good to keep track of. These carbon nucleophiles can react with, let's say, aldehydes to make new carbon-carbon bonds, which give me lots of functionality. One thing I can do with those, in the previous example I dehydrated them, but let's say I don't dehydrate them, I try to keep them here, right? If I can get to here, now I can hydrogenate both my nitrile and my nitro group to give me amines. And so now I've made 2 different hydroxyamines with a different number of carbons between the oxygen and the nitrogen. So that's a lot of control. But long story short, my pattern here, a 2-carbon amino group can come from acetonitrile, and a 1-carbon amino nucleophile can come from nitromethane.